Hello, and welcome to today's e-showcase, Inlet Monitoring for Proactive Operations. I'd like to thank today's sponsor, Hach. I'd also like to have the pleasure of introducing today's presenters. Steve Myers is a registered professional engineer in the state of Utah and has been involved in water and wastewater industry his whole career. He graduated from the University of Utah in civil and environmental engineering, and he's worked as a consultant and as a regional manager for manufacturers of water and wastewater treatment. We also have today Derek Walker, Applications Development Manager at Hach. He is based in Nashville, Tennessee. Derek holds a bachelor's degree in biological science from Colorado State University and a master's degree from University of Colorado. His career includes work in private laboratories, and he has been with Hach for 21 years with experience in product development, field training, and new application development. And without further ado, I'm going to hand the presentation over to our presenters today.
All right, thank you, Regina and Weth. And for those of you joining us live, appreciate you being on here and participating. Derek and I are going to hand the ball off a couple times, so the other one who's not presenting will be watching the chat, trying to answer any questions there. Of course, if there's any questions, we'll probably have a few minutes at the end to go over some of those as well. And to those of you joining us later on, watching the recording, I appreciate it, and definitely don't hesitate to reach out if you have any follow-up questions for us. I'm just going to kick things off with just a short disclaimer that this is an educational webinar. We're not here to specifically endorse any of the technologies or processes. This information is owned by Hach, and any personal use of copying this is no problem, of course, just to mention Hach when you do. So just to kick things off with a brief agenda on the topic today, we were talking about influent monitoring and some of the best practices there that we've observed in our experience, and maybe these are some review concepts for you. Maybe there's some new ideas for you, but appreciate you joining, and looking forward, hopefully you get something out of this. So we'll kick things off with a brief introduction about what causes influent fluctuations and what can be some of the potential consequences of these influent fluctuations for your treatment facility. We'll then pivot into some of the solutions or technologies that are available. The first grouping of these we're going to call our watchdog solutions. So these are going to be more or less some sort of measurement device to catch an event or a trend. May not be directly monitoring something specific. We'll then switch to a couple novel approaches to monitoring first organics and nutrients in influent wastewater conditions, and then toxicity, influent toxicity monitoring. And finally, we're going to wrap things up with a bit of a hat tip to maybe a bit of a topical issue here where there's a lot of influent wastewater monitoring for public health surveillance, and so a short discussion around that. And with that, we'll kick into this introduction into what are the sources of this unpredictable influent that we all have. It's a common challenge we all have, where in the wastewater sector we have to make sure our effluent complies with a specific description, but we don't have a lot of control over what's coming in. And of course, there's variations on what can be the big contributors to influent loadings. The first one and the obvious one is industries. So many industries already have their own treatment facilities and their own NPDES permits, but a good chunk of the industries in the country and around the globe, for that matter, also discharge into public sewer systems that make their way to our municipal treatment systems. So they come with their own challenges with political power sometimes and influence, and large employers. Sometimes it's hard to control this and regulate this, so we want to keep an eye on that influence and make sure that we're doing the best we can to monitor for unexpected loads from industries. Of course, rapid changes in population, whether it's a transportation hub or university towns. There's a lot of big national events or Super Bowl type activities where events that bring large crowds. These can throw our treatment systems out of whack, and many times it's related to flow, but in some cases it can be related to the loads that are coming in as well. But not only the high loads, but also underloading. So this can be where dilute water can make its way into our treatment facilities via infiltration, I&I. And staying on that topic, if you're coastal, this could also include water that's got some salinity or chlorides in it that can cause a disruption to the biological treatment process. So it's great to keep an eye on all of these sources. And then finally, we have the who knows, the unknowns. Perhaps you have a pretty predictable flow coming into a generally residential community, or coming from a residential community, but then something happens, something changes, and who knows if it's the phantom dumper or cousin Eddie here discharging into our sewers. So some of the common parameters that we're going to talk about and their implications and even the sources of them are listed on the screen here. So starting on the left, we've got nutrients, so nitrogen and phosphorus. These are coming in naturally in wastewater, but there's going to be different contributors that might have a oversharing load of this that can throw off some of the balances that we like to see in that influent. Of course, organics, this is your BOD, COD, TOC. Suspended solids is a big one, whether it's inert or includes biological or organic matter. That's important to differentiate and have an idea of what's going into your plant. And then we have the temperature, pH, conductivity. These can be good indicators as well. And then finally, toxic substances. So there's going to be constituents in the water sometimes that just inhibit our biological treatment or even our chemical treatment. And we want to make sure we have some tools in place to monitor for this so that we can prevent the impact of these on our treatment processes downstream. So as I mentioned, we just want to talk a brief little bit about what type of industry do we typically see specific loads coming from. And it's going to be different from city to city and plant to plant, but generally speaking, organics are going to be something coming from typically food or beverage, maybe chemicals, pulp and paper facilities. These can be large contributors of mainly organics. And in many cases, this can throw off the carbon to nitrogen to phosphorus ratio that our bacteria really like to see in order to perform their jobs optimally and grow and maintain balance in the system. Nitrogen, on the other hand, can come from chemical plants, metallurgy, and also food, maybe poultry or beef production. And high loads of nitrogen, they can absolutely cause a challenge when it comes to how do we take care of that through the process so we don't meet or come across some sort of effluent compliance issue on nitrogen. Phosphorus, similar. We have food production like dairies, milk producers, chemical facilities can also be a large contributor here. And then finally, toxics, going back to this topic of these can come from all sorts of different places, and sometimes they can be slow to enter into the treatment plant or very sudden. And so it's important to keep an eye on things in the influent so you have time to react. And that's going to be sort of the topic of the day, right? So with regards to wastewater treatment, it's a domino effect. If something throws something else out of whack, and it's also a balancing act that we have to perform in our treatment facilities. If something happens, let's just say, for example, a facility gets hit with a slug load of something toxic and you get a process upset. In this case, a massive one where we have the aeration tanks are foaming over the top of the walls. Well, first of all, this can lead immediately to stress for the facility management and operations teams. They've got to jump to action, highly reactive. It can be a fire alarm drill. Let's get all hands on deck and get this sorted out. Of course, if it can't be sorted out in time and there's no way to divert or direct the toxic flow, you might be putting chemicals or harsh pollutants into the environment in the discharge stream, which is never great. And of course, it can be compounded with PR issues if this is going into a highly visible body of water like a stream or river, and beaches and closures, swimming limitations come into effect. That can also be a problem. And of course, ultimately, we're looking to prevent the damage to our aquatic life and the other creatures we share this planet with in the water here. So there's a lot of implications here around the management of and monitoring of that influent, we feel. Having that leading indicator as a warning. So with that, how else would you know if you're having an influent issue? So there's a lot of different, and we don't have an exclusive or an all-inclusive list here of reasons, but influent issues can crop up in a number of ways. It can be slow burn, like your ammonia levels just continually increase, and maybe there's a slow toxic event taking place. Perhaps you're getting bleed through of some of the key parameters like nutrients or BOD or ammonia. You'll see maybe some plants are taking those grab samples out of the biology and looking at them under a microscope, and you see some of those indicator microorganisms reducing in their population, and that can be a canary in the coal mine type of warning. So there are a lot of other indicators, and my favorite here is something doesn't add up. We've all in mine and Derek's travels, we've met these plant operators and managers who really just by the smell, by the color, or just general, observations of their plant, they can tell that something just doesn't add up. It's not right. And so there are a lot of other ways that we can be alerted to influent issues. But today we're going to talk about some specific tools that we at Hach are familiar with for monitoring that. And as I mentioned at the beginning, we've broken this into three main categories where we have the watchdog solutions, which will include sampling, some basic laboratory, quick test, snapshot type of approach, as well as some online monitoring with robust products, including sensors as well as analyzers. So here we have a view of some of these that we'll be discussing in more detail. And then some benchtop solutions that's a bit of a different topic, and I'll talk about this very briefly at the end. But influent wastewater surveillance is definitely something that if you haven't heard about it already, it's definitely something that's growing in applicability. And so we have at Hach a couple benchtop solutions available to us that we'll bring up for monitoring for public health as well, not so much effluent compliance. So with that, we're going to kick off with a quick introductory poll. Which online equipment do you have or are you familiar with at your local facility to monitor influent? So this is a multiple choice question. You can click any and all that apply. So the options would be ORP, pH, temperature, conductivity, suspended solids, total organic carbon, nitrogen, phosphorus, other, or nothing. And keep in mind, when I say influent monitoring, that would, to me, be something that's maybe between your major pump station feeding the facility through the headworks and potentially up to and including the primary clarifier and maybe even primary effluent. I'll make it a broad category there. So we'll take a minute. Hopefully doesn't take too much to get some participation here on the poll question. I'll pull up my chat window, make sure we're all there. So after a minute or so here, we'll publish some results and see what the consensus of the group here is. All right, do we have some results yet, Regina?
They're almost in. Give us about 10 seconds and you'll see them.
Okay, perfect. Great. Well, thank you for the participation. It's always interesting to see, what's out there in terms of the participation in these. Of course, we'll miss having the participation from the folks who are joining us later via the recording, but we'll share some of the results here. All right, so I think I'm looking at it.
Results are in.
Let me see if I can read this. Okay, so by and large, pH and temperature, those go hand in hand. So that about 60% of the respondents are suggesting that they have pH in there, followed distantly by what looks like suspended solids and then ORP. Interesting. Or other. So it looks like it's going to be mainly pH as the indicator. Any thoughts on that, Derek, or anything you noticed with these results?
Well, I think we see that pretty often, Steve, with pH being the most ubiquitously measured parameter. Temperature also very important to the process and the biology as well. So I don't think there's anything too surprising here. Not a lot of measurement, at least in this audience, of TOC or some of the nutrient parameters, but I would imagine that's on the uptick as we see things evolve here.
Absolutely,
in the industry.
Yeah. In fact, that we have some 16% are nitrogen and phosphorus. That's actually encouraging. Many here will have some things to share. So if you have experiences to share in the chat, please feel free. We're open to that. So with that, I'll transition quickly to the watchdog solution. So Derek, actually, I'm going to have you take this one.
Sure. Thanks, Steve. You know, and we'll continue diving into some of those results that you showed in the poll there. I appreciate everybody's participation in that. And as Steve mentioned, we're talking about watchdog solutions, and these are solutions that you know, can be used as sentinels out in the collection system, very near the plant, further distance away from the plant, or within the plant walls itself in the treatment process. So these are watchdogs that can help operations and the engineering staff keep an eye on what's coming into the plant to ensure, you know, operations are running as well as they can in the process itself. We'll start with sampling, and as you probably know, if you're taking a grab sample and wanting to get a good result in a short period of time in the laboratory, it all starts with getting a good sample, a representative sample, so you know what you're taking to the laboratory is actually what's happening in the field or in the collection system. So it really starts with sampling, and in some cases, an automated sampler. You see a couple of examples here on the screen. On the lower left-hand side, a permanent sampler, which is a refrigerated sampler, collecting either at the effluent or perhaps various locations through the plant. And then the gray unit, a portable sample that can be transported out into the collection system, out into the fields, or moved around the point of the plant, at the appropriate point for taking samples. These can be very convenient because they can be controlled by flow. They can sample based on an event, such as a pH increase or a pH decrease. If there's a potentially toxic event happening or an excursion from normal pH, that sampler can begin sampling to collect either a composite sample or a discrete sample for measurement in the lab later on down the road. So they can be very useful as kind of the primary watchdog in collecting samples when they are most needed. Of course, composite samples are often collected for regulatory compliance purposes, but discrete samples can also be collected as well. Oftentimes at that particular collection point, it is useful to measure pH and conductivity and perhaps dissolved oxygen as well, using a portable meter and some rugged probes, which are also pictured on this slide. And I think many, based on our poll results, many of you are definitely doing that, measuring pH, conductivity, DO inside the plant or in places upstream of the plant as well. So it all starts with sampling and getting something good that you can measure in the laboratory within the plant. If you can move on to the next slide, Steve, we'll take a look at some of the common measurements, which we also saw on that poll list. That can be measured in the laboratory. So once you have a good sample, it is a very good practice to take those to either an operator's lab or a process control lab or perhaps a central lab at the facility to keep an eye on what's coming in the plant, how those nutrients are being transformed by various processes in the plant. And when it comes to organics like COD or TOC, monitoring how much organic removal is happening or BOD removal is happening at the facility, which is obviously one of the primary goals of the treatment process. Thankfully, with today's technology, spectrophotometers, the TNT plus chemistry, and accessories such as digestion blocks and heater blocks, all of this testing can be done in a pretty efficient format where, you know, within 15 or 20 minutes, depending on the test, you can have a very accurate measurement of, you know, ammonia or nitrate or nitrite. If you've got some industrial discharges that you might be concerned about high chlorides or metals like copper or zinc or mercury, even lead, you can get some quick tests done with these test kits without having to send a sample off to an outside lab. And that can be very useful in trending what's coming into the plant, what its effect on process operations are, And if there in fact is an issue that, some diversion might need to happen, maybe an increase in dissolved oxygen, aeration to accommodate a high slug of organics, but having more data at hand to make the right process decisions can be very useful. And thankfully, some of that can be done right there in the process control laboratory with efficient techniques like what's pictured on the slide here, without having to send those off-site and wait for a long turnaround time. So Steve, there's even other solutions available to monitor continuously in the process. I'll hand it back over to you to walk through some of those for everybody.
Thanks, Derek. No, great points. And we got a question in the chat about just, how do we eliminate fouling associated with rags or trash? I assume that question was related to the sampler intake. Put a couple thoughts in the chat there for that. But I'm now wondering if that question was more in general to, influent conditions. So as we discussed at the beginning, right? So it's, great. We can monitor the influent with some things. We get, and that gives us the biggest lead time in terms of being able to make that data actionable. But the question is absolutely correct that one of the challenges that we face in influent monitoring is this is untreated wastewater, right? There's a lot of stuff coming down the pipe, and so maintenance is going to have to be a big part of the discussion. So we're going to talk about some really robust products here and sensors, at least that we're familiar with Hach, and then provide some other tools and have a discussion around the sensor management side of things. But yeah, great question, and it's absolutely a consideration. And in all honesty, the short answer is it's going to require a bit more maintenance than what you'd be used to at other locations in the treatment process. So here I'm just going to talk about one of these first watchdog parameters. This is one of our electrochemistry products, the pH and ORP sensors. They look very similar. They use a little bit different electrodes, glass bulb for the pH, and then the metal electrode for the ORP. But these are easy indicators for just abnormal discharges entering the plant, right? These can be great for event detection. pH is a perfect indicator for starting an investigation that you might have something coming into the treatment plant to correct that, right? So too high of a pH or too low, both are not great for processes, especially the biological treatment downstream, or even some of the chemical treatments like coagulation and other physical chemical treatments that can take place. So keeping an eye on that pH. It's not surprising that many, if not most of the plants out there have this already. ORP is also one that comes up as a relatively interesting parameter for monitoring. These can illustrate perhaps anaerobic conditions, or also if perhaps an industry is discharging oxidants. Maybe there's something coming down the line that could kill bacteria, and we can pick that up with ORP as an event detector. Or it could be a slow increase over time, like a trend line. So these can be helpful tools in monitoring your influence. Both of these come built in with thermistor in there to provide accurate temperature. So that's sort of a +1 option here with either of these sensors. And for the ones we're showing here, these are the Hach differential electrode measurements. These use a 3 electrode setup instead of your traditional 2 electrodes that are used in conventional pH sensors. And the reason for this is it definitely improves the robustness, the accuracy over time, the reliability, and the less downtime associated with these, and actually reduces the maintenance. That being said, they will require some regular maintenance on these sensors, such as cleaning, and air blast systems can be added to do some of that more automatically, or at least lengthen the time between cleaning, manual cleanings. Moving on to the next electrochemical measurement, a little less common. This was also one of the lower ranking ones. I think connectivity scored 9% of the respondents had connectivity on the influent. My guess is that would be related to where brackish or salt water is in the water table, as discussed. So this would be great for monitoring chloride content, maybe I&I from salt water, or it could be runoff from communities that use salt to de-ice the roads in the winter, or other factors that could play a factor here. But unless it's something you have as an issue, probably maybe a little nice to have instead of need to have. Moving into an optical measurement here, this is suspended solids. These can be absolutely great for influent monitoring. And this solution here, the Hach Solitax sensor, this is a tool that is often used in many places throughout the treatment plant, and influent is no exception. So what you see here is some windows. This sensor uses an infrared duo scattered light method, where we are able to take a highly accurate suspended solid measurement that's independent of color, so there's no influence from the color of the water. And then we have the all-important self-cleaning wiper to keep that window clean from biological growth. We also have, it is worth a consideration, the wiper material for different types of pollutants. Fats, oils, and greases can play a factor here. And then also the wiper interval. That may be something that needs to be regulated, and even some manual cleanings built in to keep this functional and helpful. So with that, I want to transition a little bit. We've talked about some of these robust sensors that can be put in there as the watchdogs and complementing the laboratory grab snapshots. But there's also some important aspects, as we discussed, with the maintenance of the sensors and the management of them. If you throw these in there and expect good performance from them without performing optimal maintenance, you're not going to get the accuracy and reliability that would be expected or warranted. And so with this, I'm talking a little bit about some advances we've made at Hach, but clearly these are advances that are all over in the industry, and that's with connected systems and proactive diagnostics. So with our controller platform, which the previous slide is a picture of our controller, so these sensors all plug into a controller, and that's how we are able to transmit the data back to the SCADA systems, DCS, or other data management systems. We also have built in this ability to bring up what's called our mobile sensor management on our Claros platform, or software platform. And what this does is it allows operators and instrument technicians to focus on those highest priority maintenance activities first. So this will give easy step-by-step directions, as well as proactive and time-based alerts for specific maintenance procedures to take place to ensure that your instruments are up and running with high accuracy as much as possible. A few ways that this is achieved is first, step-by-step visual procedures. So no need to go get the manual off the shelf, or even maybe set this up in the asset management system. It can do this proactively with alerts. And once the operator or instrument technician is out at the instrument, it can walk through with some detailed visuals of exactly what the step-by-step maintenance procedure looks like. In addition to this, complementing the laboratory discussion we've had before, a lot of these online instruments do require some level of calibration or validation to keep the accuracy up. And with the mobile sensor management, we can sort of link the lab with the process highly efficiently by, for example, here would be a sensor that's, you can take a grab sample at the same time as you're doing a measurement validation, and you can actually send to the lab the measurement from the online device while you're taking the grab sample to the lab. And as soon as the lab is able to process that lab measurement, you can compare and contrast what the measurements are between the two instruments, or between the lab and the online instrument, and in many cases upload a calibration to the instrument based on the laboratory reading. So this helps streamline the SOP for those specific online instruments, and essentially keeps a log of when and how often this is done, and tries to make this as easy and streamlined as possible. So with the wrap up of the online sensors, we're going to transition to some a bit more beefy solutions and some analyzers here. So I'm going to kick things off with with what we have here, and there's other online organic carbon monitoring solutions out there, but the one that Hach is familiar with is our Biotector B7000 solution. So this unit here is capable of measuring, very low to very high organic loads, up to 20,000 milligrams per liter of TOC. It's available to be configured for TOC only if organics is your main concern, but also there's the potential to add on total nitrogen and or total phosphorus as a measurement as well internally to this unit. So it's possible to combine these so that or set these up, configure these to measure multiple sources of influent as well. So if you have the ability or location to and desire to monitor multiple sources, these can be set up to sequence between multiple channels, 6 for the TOC only and up to 3 for the TOC with TN and or TP as well. And like I mentioned earlier, these were specifically designed to manage very dirty water. So this is not going to be something that shies away from those influent locations where you might have solids and some challenges. And so how does this robustness get achieved? So these biotectors work using what we call our two-stage advanced oxidation process. This is a very strong basic digestion in the liquid phase at room temperature. And because we're doing it at liquid phase, we can use a relatively large volume. This helps us make sure that sample is representative, first of all, to maintain accuracy, but also allows us to use relatively large tubing in the device so we can bring up to 2 millimeter soft particles in there and fully oxidize them and get some accurate results. Also, it's set up to do automatic cleanings with acids between every measurement cycle. And all this combines together to have a pretty long maintenance interval. So every 6 months when reagents are being replaced, it would be a maintenance cycle. And this has been certified by independent organizations for 99% plus uptime, which means there's about 12 hours per year of planned downtime for maintenance. So low maintenance, but high robustness in this type of an environment. And just a quick description of this two-stage advanced oxidation. I'm going to run through the steps here. So before the main oxidation, the sample is mixed with an acid in a reactor. And this then purges all of the inorganic carbon out of the sample in the form of carbon dioxide, and it's also measured. So we're also getting a measurement of the inorganic carbon, which is usually interesting, but not all that helpful in many cases. So after that starts, we get into the first oxidation phase where a base is added to the sample and the ozone generator is kicked on. This forms hydroxyl radicals in the sample. These are very strong oxidants and oxidize all that organic matter into carbon dioxide, runs it through the detector. Actually, the second phase of this oxidation is when acid and a catalyst are introduced into the reactor to complete that oxidation. That's just making sure that everything is turned into CO2, and then it's run through the detector, and we get the TOC result calculated out of that. We can, and as I mentioned before, we can also oxidize nitrogen to nitrate and measure that with photometric measurement using UV light, and TP using the vanadomolybdophosphoric acid method in the reactor as well to get the accurate TN and TP measurements. And as we're talking about influence, every influent has different challenges. So based on what is the challenge of that influent, is it fats and greases that float to the top? Is it sand and grit that sink? Combinations of the two, or is it a location issue where we just can't put the unit where it is convenient and we have to pull a sample a relatively long distance? We have a lot of options for sample delivery and sample conditioning. So whether it's sand traps, or on the right here is a Venturi sampler. This allows us to bring in, even with solid particles, a decent volume of sample from very long distances up to 40 meters or about a couple hundred feet almost distance away to the unit itself. So with that, I want to cover a couple quick case studies or site histories here. So the first one is in Europe. This is a plant in the Netherlands in Uwen. I think I'm pronouncing that correctly. This is a relatively large city, 350,000 inhabitants, and they have a few large industrial dischargers. So at the starting point of this project, they didn't have anything monitoring nutrients in the influent or the effluent. So they suffered a little bit from unpredictable spikes. They were using a third-party lab sending their data, but they found that was not quite quick enough turnaround to manage the periodic slug loads of various mainly nutrients coming into their process. And this led to some exceedances in their effluent of phosphorus in particular. And it was a costly issue for them to restore the treatment process as well as manage the compliance for their effluent. The solution that was installed consisted of two of these B7000 units, the TOC, TN, and TP, so doing the nutrients as well. One at the inlet and one at the outlet. You can see here on the right a view of one of these in their weather-proof enclosure. This allowed the plant management to have a lot more information coming a lot more quickly and time to react to it. So not only could they make process changes to react to these spikes, but they also were able to root cause the contributors a lot more quickly and effectively based on the parameters that they're seeing spike in their influent and the quickness in which they're able to reach out and connect with these industrial dischargers. So long story short, since they've been installed, they've been working reliably, and based on that ability that the plant now has to react to these this data stream coming from these online instruments, they roughly give a measurement every 12 minutes. They were able to essentially meet permit consistently since these units were installed, and they were able to have this visibility into their influent. Second quick one here would be a North American example. This is a facility in a very cold weather climate in North America. Here we have a couple pictures. This is a bit different approach where instead of monitoring at the inlet to the treatment plant, it's actually monitoring the main lift station that feeds the treatment plant. So even prior to the full headworks. This solution consists here. You can see the sampler and the black refrigerator in the center bottom, and then the TOC analyzer doing TN and TP on the right-hand side with the reagents below. And if you come around that corner, you can see the biotector there on the left now facing to the left, but they have this instrument trough here where they now have ability to measure suspended solids in real time, pH, conductivity, and oil and water. And these all connect to one of the cloud-based control systems or controllers and provide a visual input to the management of the facility, as well as real-time readings and these proactive diagnostics and instrumentation health readings, essentially feeding the cloud platform. And so here's an example of what that looks like, whether you're on an iPad or looking at this on your computer screen, and the ability to download some of this real-time data. So with that, I'm going to close the discussion around total organics and the correlation. I did want to mention really quickly that while we're talking a lot about TOC, maybe the question comes up, well, I'm more interested in BOD or COD, and those are some parameters we're maybe a little bit more used to. You can get a pretty decent correlation of TOC to BOD in many cases if you have relatively consistent characteristics. So this can be a good event detection, but it can also serve well as almost a trend chart for your organic loading, of course. The rule of thumb is about the TOC number is going to be roughly 40%, 40 to 50% of the expected BOD number in terms of milligrams per liter concentration. So just a quick FYI there, and that I'll hand it to Derek to cover some toxicity.
Yeah, thank you, Steve. Appreciate that. We're going to transition from talking about organics and some nutrient parameters that Steve mentioned and highlighted in those case studies to talking about influent toxicity. This is a newer method of measurement and kind of an evolving trend that we are seeing, as well as some new technology that's able to do this as well. So on the next slide, I want to just provide a quick clarification. If you can forward that slide, Steve, there it comes, thanks. And talk about the difference between influent monitoring for toxicity and effluent monitoring for toxicity. So many facilities, especially on the compliance side of things, are familiar with wet testing or whole effluent toxicity testing. This is done this is carried out because it's on many permits to do toxicity testing of that effluent, and the organism that you see on the slide is the Cerodaphnia organism in invertebrate, which is often used in these wet tests. We want to speak about for the next few minutes, and what I'll be mentioning is on the influent side, and specifically influent toxicity. So we're not talking about the whole effluent testing here. We're going to be speaking about the other side of the plant on the influent side. So just wanted to set that expectation that and just prevent any confusion about the word toxicity, because they are two very different things. Next slide, Steve. Many of you know that there are toxic events that can happen at the headworks or even upstream in the collection system that can have a pretty dramatic impact on the biology of the facility and the biomass in your facility. And we're going to speak about that type of toxicity that happens when, you know, a toxic slug of a material or chemical or even highly concentrated waste comes into the facility and affects the activated sludge and the biomass. This can affect the biology in the plant in several different ways. First, by inhibiting respiration. So the metabolic activity of the activated sludge can be hindered by whatever substance or some very specific substances that are coming into the plant. When this happens, they lose their activity. Maybe they lose their ability to remove BOD from the system and from the waste, or other effects that we can see there. The second is through inhibition of nitrification. So those nitrifying bacteria, which are very important in converting ammonia nitrogen to nitrate and nitrite, therefore removing ammonia from the system and maintaining permit if you've got ammonia on your permit. These toxic impacts can inhibit nitrification, which obviously has multiple effects downstream. The third type is what we call shock loading of the system, where either a high strength waste that includes, you know, high levels of organics or nutrients can also affect the biology in the plant, sometimes actually accelerating their metabolism, where they consume a lot of dissolved oxygen, which obviously has a cyclical effect of removing DO from the activated sludge and therefore, you know, causing damage to the biomass that way. Whatever the inhibition type, they can have, you know, significant impact and be at risk to the plant. Obviously, if nitrification is inhibited, there are some potentially regulatory violations. If BOD is not being removed through the normal process, then it could also be some regulatory impacts there. But, you know, significant process upsets can occur that can take quite a bit of time to recover from, and obviously involve a lot of cost, not only to operational costs, but also, you know, the cost of potentially reseeding the plant with new activated sludge. So we want to avoid those risks and have a good handle of what's coming into the plant so that those upsets can be prevented. You go to the next slide, Steve. Talk about some ways that metabolic rate can be monitored. The respiration of the activated sludge and the biomass in the plant can be monitored by looking at the respiration rate of that sludge. That respiration rate is typically monitored by a technique called respirometry. This is using a dissolved oxygen probe, and you can monitor the oxygen consumption of that activated sludge over a period of time. And this can be done either in the laboratory or now can be done in the process. What you see here on this chart is a kind of a bench scale experiment where a couple of liters of activated sludge were placed in a container, and the oxygen consumption was monitored over a period of time, while every 20 minutes or so this toxic substance with a code name of 9565 was dosed in various concentrations to the sludge. And you can see that over a period of hours, each time this toxin was administered to this pilot batch, that respiration or consumption of oxygen was dramatically impacted. Sometimes it happens very quickly. When that third dose of 100 microliters was added, you can see a significant drop in respiration. Sometimes it happens a little bit more slowly. But when that inhibition of respiration occurs, the BOD removal or the nitrification can also be impacted. So this is just a nice bench scale pilot chart to show how dramatically that biomass can be affected. Steve, if you move to the next slide, there's a couple of different ways we can do this in the process lab. And typically those are respiration-based methods. You might have heard the oxygen uptake rate test done before, and that is certainly done quite often and probably something you've done in your own facilities. But respirometry or that OUR test allows us to quickly and efficiently kind of monitor the metabolic condition or quote unquote health of the microorganisms in that activated sludge. And if we measure that respiration rate, it gives us a good indicator of how healthy they are. Next slide, Steve. So typically this is done with direct measurement using a dissolved oxygen probe. A known quantity or volume of activated sludge is in a beaker or in a sealed vessel. And then that dissolved oxygen measurement is taken over time, and you can calculate the respiration rate by seeing how much oxygen is consumed. And according to the formula here, calculate that rate based on the time of that measurement as well as the volume of sludge. And this is typically what's done in that oxygen uptake rate test or SUR tower if you're using the specific oxygen uptake rate test. But that's done with a respirometer. And on the next slide, Steve, we will see several different types of laboratory tests that can be run or specific technologies. Of course, a BOD probe can be used with an automatic stir to stir the sludge. The BOD5 test, this uptake rate test is done over 5 days to correlate with the BOD5 method or the CBOD5 method, and that is measuring oxygen consumption and then converted to milligrams per liter of BOD that is consumed. Alternatively, you can use an automated instrument for process control. The BOD Direct Plus is pictured here, or the BOD Track 2. And some of the unique features of these instruments is that you can do some experimentation and actually modify the time period that these oxygen uptake tests are run, so that it can give you some process control data using an automated laboratory instrument. On the next slide, you'll see how this technology can actually be brought into the process. So grab sample of sludge no longer needs to be taken back to the laboratory, but it can actually be sampled directly from the influent streams as well as the aeration basins and measured using a process analyzer. This process analyzer is a Hach unit, and it's called the EZ7900 influent toxicity analyzer. And this actually enables facilities and operators to measure real activated sludge without grab sample and doing a continuous measurement where a data point of a toxicity index is gathered every 15 minutes. So dynamic changes to the activated sludge or the biomass can be trended and measured on a continuous basis. It provides an in situ measurement, which has not been able to be done before. And since in situ provide a real early warning to any toxic influent that may be coming down from the collection system or from an industrial discharger, or even a high strength waste stream that gets brought into the headworks. So really allows corrective action can be taken before it's too late, before that biomass is significantly inhibited or damaged, causing an upset. Next slide, Steve. I'll show you over the next series of slides, how this technology works and why it's a benefit with a case study that has recently used this technology. So we are doing a respirometry, and we are are taking a measurement of respiration rate by use of a dissolved oxygen probe in this instrument. It can be multiple influent streams can be sampled. So if you've got either a septage dump or multiple influent streams from the collection system, each one of those can be sampled individually and brought into the instrument on a cyclical basis. You can actually monitor multiple influent streams at the same time. The data, that toxicity index data can be sent via analog signal or digital signal to a SCADA system or other data management system so that that trend line can be plotted over hours and days and weeks and even months, of course. So it's a very useful early warning system that can provide a great baseline of what normal operations look like when an event is not occurring. The sampling system and the filtration system is a very critical part of this offering. Obviously, you want the right sample to be taken at the right time, and it needs to be a filtered sample since we're dealing with sludge here of different concentrations. So you use a couple of different panels. One is dedicated to the aeration basin, and that is an automatically cleaning paste sampling system and filtration system that pulls that sample directly out of the bioreactor. And then another filtration system is dedicated to the inlet streams. That could be one inlet stream, that could be 2 to 4 or 5 inlet streams, and that is conducted. That filtration and sample sequencing is done by the panel that you see on the left side of this photo. And then those sampling systems feed filtered sludge to the analyzer at the right time so that toxicity index can be measured and then the data sent back to the trending system or the SCADA system. Go ahead, Steve. I think in the interest of time, we'll probably move through a couple of these slides pretty quickly. And I'll just note that 4 different measurements are taken and calculations are done when the first reference sample, which is the normal activated sludge, is pulled into the system, and a DO measurement is taken, and then that healthy respiration rate is used as the reference value. In the next slide, you'll see that after that reference value is known, that activated sludge sample is spiked by the influent stream. So a small dose of the influent stream is added to that. Another DO measurement is taken over a 15-minute time period. And at the end of that time period, a second calculation is made, which is kind of the toxic respiration rate, which is done in the formula that you see at the top of the page. And then that toxicity index is calculated, which gives the percent inhibition rate by comparing that toxic influent or potentially toxic influent respiration rate to the normal respiration rate that is typically seen in the activated sludge in the aeration basin. So it's a very automatic system that gives you that toxicity index every 15 minutes. Next slide, Steve. We'll kind of begin to wrap up this section by showing how this is used in real time with a case study from the wastewater plant of an industrial discharger. Pretty standard plant layout. They do pH correction in a tank at the influent side of the plant, and they have a couple of calamity tanks or emergency EQ tanks over on the right-hand side, and they are able to divert waste if they see something coming into the plant, which would affect the activated sludge or the biomass. In the chart here, you'll see that the EZ7900 influent toxicity analyzer is used to trend that toxicity index over time. So this trend line is built every 15 minutes, and they have an early warning alarm set at 70% inhibition. So if they see the respiration rate of the biomass slowing down and it reaches that 70% level, that sends a warning to the operators that they need to keep an eye on that influent. If it reaches 85% inhibition, then they know that they have to divert that waste to their EQ tanks immediately so that they don't damage the biomass in the facility. Now, initially, they set that early warning at 50% inhibition, but they saw that even between 50% and 70% inhibition, the biomass in the aeration basin was actually okay. It wasn't being inhibited based on other measurements that they were taking. So they raised that alarm value to 70%, which allowed them to better optimize the process and only divert waste when they absolutely had to prevent that upset in the plant. And so just wrapping up on the next slide, you'll see that there's some significant benefits. Obviously, they only have to divert when they need to, and they don't have to shut down the plant or, due to an upset or, a potential upset. They can bleed that waste into the aeration basins on a very slow trickle so that they don't damage their biomass. And obviously, this leads to improved operations and more uptime, not only of the wastewater plant, but of the surfactant production at the main facility as well. So this is a new emerging trend, new technology that has proven very beneficial to manage that influent streams and prevent toxic shock events or other upsets to the wastewater plant. Steve, I'll hand it back over to you to wrap up.
Yep, we'll wrap up. And like I mentioned briefly at the beginning, we're just going to talk a little bit about wastewater surveillance. So I was listening to a podcast by the Words on Water podcast, and they had a rebroadcast of a webinar with Dr. Amy Kirby. She's the CDC's National Wastewater Surveillance System lead. Maybe you've seen some presentations of hers, and they also had Dr. Andrew Sanderson, the WEF Medical Chief Officer. But they talked a bit about this, and it's interesting that this still is a topic. We know that we're all getting sick of it, but believe it or not, there's been some, role that sewage has played in the fight against our pandemic and in confirmatory data for the clinical testing, or even giving us early warnings to waive, outbreak events, or as maybe we're peaking and we can get things back to normal. But believe it or not, there's some valuable data in the wastewater. Now, this is, again, a different direction than we typically would be talking about here in protecting the downstream processes. This is more just information for public health. And just wanted to provide a quick FYI to the group here. And of course, if you have any questions, please reach out. But Hach has played a role in some of the technologies being used right now by many communities that are sampling their wastewater for monitoring the COVID virus. We have a couple solutions. We know that this isn't something that plants want to buy. Typically, it's more driven by grants and health department funding, but we do have a few solutions here for monitoring using PCR, similar methods that is used in the clinical side of the business. But in this case, we take samples of wastewater and we can condition that and prep it, and then measure it for the genetic fingerprint, if you will, of the virus. And in some cases, these can then go on further to look into variant tracking or confirmation of variant tracking in our communities. So we have here our gene count solution. This is going to be a relatively simple prep. There's some pipetting involved here. We call this a medium to good sensitivity. It's a laboratory environment type of product, and it can do multiple tests at the same time in the PCR device, as well as the Gene Expert solution here. This is a simple one-step analysis, great analytical sensitivity, but relatively low volume. It's 1 to 3 or 1 to 4 tests depending on the model here. But just wanted to sort of hat tip that this is something that's also being looked at in the influence of our wastewater plants and helping our communities broadly with some interesting problem solving that's not generally the purview of our profession, which is to protect the water bodies. This is more to inform our public health decision makers. So with that, we left all of about 0 minutes for questions, so we appreciate the chat feed. But if there's any questions, please feel free. As long as the host gives us time, we're happy to stick around and answer them.
Sure, I think you guys did a great job in the chat feed responding to several of those questions. But if anyone has any questions, please go ahead and take that time to post those in the chat. We'll take a look. We'll stay here for a few moments. Derek, Steve, if you see anything come through, go ahead and grab those and we'll respond.
Well, will do. And as well, I'm keeping an eye on that. I definitely want to thank WEF for the platform here, and of course the attendees and anybody who's listening to this live or later. Thank you for your participation and attention. We appreciate it.
I'm just going to look
One of the questions, Steve, that we did not get to was from Tom, and he asked about how often needing to clean and calibrate the ORP and TSS sensors. Do you want to comment on that? If we run out of time, we can certainly get back to him by email on that as well.
Yeah, sure. We can respond in email. It's going to be, your mileage may vary. It depends. Like everything, there's going to be some rules of thumb. And for me, it's in an influent environment, we're probably looking at manual wipe down on a weekly basis, and it might be something you'd want to look at even more frequently based on performance. One thing I like to note is when it comes to pH sensors, people can be a little sensitive to what they use to wipe down the bulb, but with an ORP sensor, a bit more aggressive elbow grease is totally okay. So I definitely want to suggest that a bristle brush or something, not necessarily wire bristles, but a good toothbrush type of bristle brush is okay on an ORP sensor.
Thanks, Steve.
I think there was one also a question around the maintenance on the filter panel, the 9100 for the toxicity analyzer.
Okay. Yeah. So the obviously that panel is filtering sludge, and that can be anywhere from 2 to 8% solid, so can get reasonably thick. Typically, not typically, but those are self-cleaning panels, and it gets rinsed with plant water after every single filtration cycle, and it keeps that stainless steel filter that you may have seen on one of the slides very clean. In multiple installations around North America, we observed those pretty quickly, and that stainless steel filter, due to the rinsing with plant water as well as an air scouring that happens, there's instrument air that's plumbed to each of those filtration panels and actually back flushes that filter with air while it's being scoured with water at the same time. So it's a very powerful cleaning cycle, and typically does not require much maintenance. Every, I don't know, let's say a month, perhaps, that filter needs to be removed from the canister. It's a permanent filter. It needs to be removed from that canister and just wipe down that mesh screen in case there's a rag or large chunk of solids that is wrapped around that. But typically, I would say monthly or every couple of months would that need to be happen. So the self-cleaning features make it very robust. And then the dissolved oxygen probe itself also gets scoured with air so that its cleaning cycle is simply a wipe down, every couple of weeks or so inside the instrument. So both very robust and designed to operate in an environment where it's constantly measuring and filtering activated sludge.
Well, thanks again.
Yeah, it looks like we are wrapping up. Thank you again to WEF and to all of our attendees today, both live and on demand. We appreciate your participation.
Yeah, this was great. I actually think that you all were able to respond to all the questions in chat. And I want to take this time to thank Steve and Derek. This was a wonderful e-showcase. And we certainly want to thank our sponsor, Hach, for sponsoring today's event. This actually concludes today's e-showcase. Thank you all for attending. The recording will be available at wefbuyersguide.wef.org. We will send all registrants an email tomorrow with that link. And please Visit our event calendar to sign up for future events.